Good morning all. For this particular session, I am Satish signing in on behalf of Department of EEE. I work as an assistant professor in St. Joseph's. The session for today, what we are going to see is all about introduction to electric circuits, or we can say the basics of circuit analysis, what is behind every component which builds the electronic circuits, etc. We are going to see for today. So as I mentioned, this is all about introduction to basics of circuits and analysis. The first question what comes to our mind is like the fundamental components of circuits. We all know about resistors, inductors and capacitors. What is resistor, what is inductor, what is capacitor, and why it is said as the essential components of any circuit. If you take, see, when we deal about big circuit boards, the components what we likely see will be made up of different voltage sources, maybe a potential divider circuits, maybe a driver circuit, maybe a power electronic circuits, maybe a transistor, diodes, rectifiers, all will be aligned together. But even though we have all these, we can make a segregation for an electrical circuit components as such as active and passive. So the basic components can be split into two, one as active and the other as passive. So active components has the ability to store energy and react to that stored energy. Based on that, it will create some changes in the output voltage or the current waveform, etc. So when we go for passive components, it doesn't store any energy, but it does create some changes in voltage as well as current. So the basic classification of any electric circuit components can be taken as active and passive. So followed by, when we move into the different approach on the types of components which are present in circuits, we have storage elements, that is inductor, capacitor, etc. We have energy discharge capable elements which are resistors, as we know. So the notation for a resistor as we speak, a resistor is represented as, this is how a resistor should be notated. We have the representation as a symbol for the resistor. So it is represented by resistance R. R is given by rho times L by A, where rho is resistivity with respect to a material. L is length, A is cross sectional area. Okay, so the first component what we are going to study is resistor first. You will understand what resistor is, and then we'll move into the active components or the storage components like inductor and capacitor. And after that, after knowing all about inductor and capacitor, we will move into the analysis part, where how a circuit should be visualized, or what are all the analysis that we can do or perform inside any circuit. Okay, and then we will see with respect to DC, and then we'll go for AC. Okay, so the first component is a resistor. A resistor is given by a notation like this: R is equal to rho L by A. Rho stands for the resistivity with respect to a material. Say for an example, if a copper material is chosen with respect to a copper, the resistivity will change. If it is an aluminum, the type of material, then the resistivity for that particular material will also change. So with respect to that, we have some specific resistivity concerned to a material, and the relationship for the resistance which is being calculated is given by rho L by A. So L is the length of the material, A is the cross sectional area of the material. So even if I take copper as a material with a specific resistivity, the length if it changes or the cross sectional area if it changes, then it affects the overall resistance which is being calculated. Say for an instance, I have one copper wire capable of providing some 5 ohms. If that 5 ohm resistance is being stretched, or if it is being contracted, or if there is any change in cross sectional area, then it is need not like the same 5 ohm exist. The 5 ohm tends to change. So that is the idea behind how a resistor functions. So again I'm saying, with respect to rho L by A, where a direct relationship is with respect to length and inverse relationship with respect to cross sectional area. So if length increases, resistance increases. So if length increases, it makes resistance to increase, or if it decreases, again, then the resistance tends to decrease. So we may think this is a simple phenomena, but any sensors based on resistance, resistive changes works on this principle. Say for an instance, you must have studied about the latest weighing instruments likely made up of strain gauges. In strain gauges, if you put some weight, what happens inside? So the strain gauge are nothing but resistance wire based sensing element which carries many resistance wires connected together. So when we put some weight, the deformation likely affects what? The length or cross sectional area of the wire, which again in relation changes the resistance. So we may think it as a simple resistor, but it has some relationship with some greater things like a sensor I said, likely to be a strain gauge. It has some input for that. So the fundamental is very important. So length is directly proportional to the resistance of the wire we take. So if resistance tends to increase, length increases, resistance increases. Length decreases, resistance decreases. So it has a direct relationship. So here you find direct relationship. Then when we go for cross sectional area, so if cross sectional area increases, what happens? This affects the resistance to decrease. Okay, so it is inversely proportional. So when cross sectional area increases, resistance tends to decrease. So it is completely inverse to each other. So if area decreases, cross sectional area decreases, then your resistance tends to increase. Okay, so hopefully I have given you the points which are important for a resistor alone. So in resistor, R is equal to rho L by A. If length increases, resistance increases, direct relationship. If area increases, resistance decreases. If cross sectional area decreases, resistance tends to increase. We call this as inverse relationship. So rho is the resistivity of the material. So this is all you need for a resistor. So when we supply a resistor with voltage and current, the phasor relationship we say. So if I give voltage and current, see this is an DC voltage and DC current being represented with respect to a time. It is all along as a unidirectional input of current as well as the voltage. So it maintains a steady state value for all the time. So a resistor has this voltage and current being given as an input, then it does not create any change in the phasor relationship. So the phasor relationship for a DC tends to remain same, V and I, with respect to a time. The phasor relationship doesn't change even if it is an AC waveform. If I have V and I and alternating current being supplied, then here also the phasor relationship doesn't change, which is there will not be any difference between the phase angle between voltage and current. So hopefully I have made the point on how the resistor behaves. So there is no change in phasor relationship. Maybe the magnitude of the voltage or current may get altered since it is a dissipating component, but the angle between voltage and current will not change for a resistor. So this is all about resistor. Secondly, what we are going to speak next is all about inductor. So what is inductor? What does it do? What is the role of inductor? That is what we are going to see next. So inductor, the notation is L. This is how an inductor is being represented. Okay. So for inductance, the L value can be given based on XL. XL is equal to 2 pi F times L. So what is XL? You can ask me. So in previous, I forgot to mention, for a resistor, the unit is represented in terms of ohm. Okay. For resistor, the unit is represented in terms of ohm. For an inductor, it is going to be in terms of Henry. Henry it is. So this parameter we call it as inductive reactance. This may sound different, or you may have a confusion. What is inductive reactance and why do you put Henry here? So for resistance, the unit I said as ohm. For inductance, the unit is H. But if I want to find an equivalent relationship with respect to resistance, inductance, capacitance, for identifying the or realizing the work of all these three components inside a circuit, we need reactance to be calculated. So this inductive reactance is represented in terms of ohm. So please listen again. The resistor's unit is ohm, inductor's unit is Henry, where we are deriving an inductive reactance which is again mentioned in ohms, so that I could equate a resistor with respect to an inductor. A notation can be made. This we call it as a complex number representation. J is an imaginary parameter. Okay. So this R becomes real, J represents imaginary. So XL along with imaginary creates a complex number. Okay, you can ask me why we need to use a complex number. Why should we relate resistance with respect to an inductor? Why does it all happen? For a DC circuit, for a steady state, we don't have much characteristics exhibited by an inductor or capacitor, because the steady state value of the voltage and current remains same for an infinite number of time. That is what we assume. So practically the changes at the initial point or after steady state will not have much changes over the relationship, phasor relationship between voltage and current which passes through an inductor or capacitor. But when we go for an AC circuit, this AC circuit will have phasor relationship between voltage and current. So the AC waveform with carrying a voltage and current, if it is given to an inductor, and that passage of voltage and current will have a phasor difference between voltage and current after it passes through an inductor or a capacitor. So for that sake, if I have a collective component of resistor, inductor and capacitor in a circuit supplied by an AC waveform, then there is a possibility or a high chance like it will create an equivalent circuit carrying a different phasor relationship together by the action of a resistor, inductor and capacitor. So to analyze the same, we need a representation with respect to one complex number. So as I said, the phasor relationship is being given by an imaginary part. So this XL will give me a phasor change over voltage and current, a difference, and that is being represented as an imaginary part. So that we will study. So the representation of XL is equal to 2 pi times 2 pi f times L. So now if you ask me what is F? F is the frequency, L as the inductance, so XL will be the inductive reactance. So 2 pi f we represented it as omega, or in simple terms omega L. So this is what we call it as a frequency component. That is why it behaves differently in an AC circuit. With respect to a frequency, the inductive reactance will change. Say for an instance, I have a very high frequency waveform. A frequency is very much higher when supplied to an inductor. Then what happens to my inductive reactance? So this affects XL to be higher for the same L value. Hope everyone understands this. The inductor's L value can be constant, but if frequency increases, the effective inductive reactance tends to become higher. So inductive reactance increases as frequency increases. Similarly, when frequency decreases, the inductive reactance will also tends to decrease. Now coming back to the inductor, what does an inductor do? Inductor, we know that it is a storage element. A resistor is a dissipating element. When you supply voltage and current, it tries to restrict the flow of the current so that it creates a drop across it, as well as it provides a heat dissipation over the component. That is how it is trying to limit a current flow. Similarly, an inductor is a storage element. When a current passes through it, it tries to store the charges in an electromagnetic field. Whereas when we go for a capacitor, see, it is being represented with two lines. The representation notation is C and the unit is farad. Again, XC is the capacitive reactance and it is given by 1 by 2 pi times F and C. So again it is represented 1 by omega C. Same relationship with respect to a frequency, with the frequency is going to alter the overall capacitive reactance. So this we call it as capacitive reactance. And the unit is again ohm. So you must have understood now. Resistance unit is ohm, inductive reactance unit is ohm, capacitive reactance unit is ohm, whereas the inductor's unit is Henry, capacitor's unit is farad. So this is all for your understanding. So the inductor tries to store the charges in electromagnetic field, and it creates a phasor relationship between voltage and current if it is an alternating current which is being passed in. Similarly, a capacitor also tries to create a phasor relationship between voltage and current if it is an alternating input being given. Okay, so now again we compare inductive reactance and capacitive reactance. What we get, again, F is a frequency, C is the capacitance. Now F increases, the effective capacitive reactance decreases, F decreases, Xc increases. So now you must have understood, even though the capacitor is held constant. So similarly, if inductor is also kept constant, it doesn't matter. If frequency increases, inductive reactance increases. If frequency decreases, inductive reactance decreases. So if I have this complex conjugate being represented for an inductor, I use R plus J times XL. This J is going to be positive. I will tell you why. Here, if it is being represented with a resistance, we used to represent by minus J operator. I will tell you why. What is minus J? So this is all for your basic understanding about inductor and capacitor. So capacitor tries to store again the charges, but in an electrostatic field. And you know how the capacitor behaves. We have the formula for it. See parameter calculation with respect to epsilon, again the permittivity of the medium between free space, and all we have studied in the physics. So I'm not going to cover that, but you must have understood now. Inductor is a storage element, capacitor is a storage element. It stores energy in an electromagnetic field, it stores energy in an electrostatic field, but it may look similar, but the J operator here is different. Why? That is what we are going to see next. So the phasor relationship, that is because of an inductor, will be like this. It creates a relationship between current. When we have in phase relationship of voltage and current given to an inductor, it creates a phase difference of plus 90 degree. Okay, so which is the current falls back by 90 degree, that is voltage leads, current lags. So this is how an inductor behaves. So in capacitor, the same relationship will happen to be like this, minus 90 degree. So this we call it as lagging factor. The current leads, voltage lags. Here the voltage leads, current lags. So let me brief it. Voltage leads here, current lags. Current leads, voltage lags. All this happens when an inductor or a capacitor is put to an alternating current, an AC quantity. So for representing plus 90 degree, we use plus J operator. For representing minus 90 degree in the phasor relationship, we use minus J operator. So this is how for inductive reactance and capacitive reactance it acquires plus J operator and minus J operator. For your understanding, this is how the phasor relationship is. Whereas for a resistor, finally the relationship will be same. There is no difference between voltage and current phases, that is the angle, so it remains same. There is no current lag lead, nothing will happen in a resistor, so it remains same. Whenever you provide an alternating current to a resistor, the phase are different, retains same after it passes through out. So this is all about your understanding for inductor, capacitor and resistor with respect to an alternating current. Now I will brief you some. So inductor's unit is farad, inductive reactance unit is ohm, capacitance unit, inductance unit is Henry, my mistake. Capacitance unit is farad, capacitive reactance unit is ohm, the resistance unit is ohm. So this is all about the consolidation of the three basic components: resistor, inductor and capacitor. While the inductor and capacitor has the capability of storing energy, where resistor only dissipates the energy as a heat. Okay, so this is all about the understanding of resistor, inductor and capacitor. So next what we are going to see is all about the types of sources. We say voltage source, we say current source, we say source. What is the difference? What is the difference does it make? So that is what we are going to see. So as we start, what is source? Source is one which supplies energy. So source is the one which supplies energy. There are different notations which are being used. Say for an instance, this is how a voltage source is being represented. So this represents an voltage source. This represents an current source. Okay. What is this? This is also an voltage source. So what is the difference between all these? Why it is called as voltage source? Why it is called as current source? And what is this notation? This is an DC voltage source, DC current, and this is an AC source, AC voltage source. Okay, so this is all about the notation of a source inside an electric circuit. So why it is known as voltage source, why it is current source, why this representation needs to be given as a sinusoidal, all we will see in detail. So when we talk about voltage sources, this voltage source tries to give the potential as constant. Say for example, I have a voltage source like this which gives a value of 30 volt, which means it is going to try to keep 30 volt fixed, but what varies? The current varies. The current varies. This is what a fixed voltage source is meant about. When we go for a current source, say for instance, it is happened to supply a current source of 10 ampere, which means it is able to keep the current value 10 ampere fixed. What varies? Voltage varies. This is how the understanding between a voltage source and current source should be realized. So when we speak about voltage source, the voltage is being held constant. What varies? Current varies. In a current source, as we speak, the current value will be kept constant. What varies? Voltage varies. So at times in a network, if we happen to put a source inside it, it is going to compensate both for voltage as well as current. That is the overall logic behind any circuit analysis. So a source, if it is being put, it is going to compensate both for voltage and current. But if it is able to keep voltage as constant and vary the current, we say it as a voltage source. If it is able to keep current constant and the voltage varies, we happen to say it as a current source. This is all about the DC voltage sources and current sources. When we go for an AC source, the notation is given as sinusoidal or the reverse. Both stands for an AC, because we choose an AC waveform to be a sinusoidal one. If you ask me why we choose a sinusoidal waveform, we have many waveforms in an AC. Say for an example, this is an AC waveform of sinusoidal, pure sinusoidal wave. Next, we have a square waveform. Next, we can also have a triangular waveform. Next, we may also possess what we say, this is triangular, and this is B, this is C. We can have a sawtooth kind of waveform like this. No, it is not sawtooth, but happen to be a different kind of an AC waveform. All these are AC waveforms, but we choose a sinusoidal one. That is an explanation behind everything, but let me explain you. All these are AC waveforms. A square waveform is also an AC because it happens to traverse with respect to a time interval. Say for example, all these time intervals are same. It happens to possess the same frequency. Frequency is same, 1 by t for all the 4 waveforms, sinusoidal, square, triangular, and the last one too. But the nature of the waveform, when we look about the sinusoidal one, the change is what we seek at each and every time intervals. That is what really matters. So here you find a change in magnitude of smooth transition from 0 to maximum, maximum to 0, again to negative maximum, and again to 0. This is what happens in an sinusoidal one. For a square waveform, again, it is constant till the time t, so it is maximum over a time period, and after t it becomes negative maximum. This is what a square waveform exhibit. For a triangular, again, it is 0 here, it is maximum here, again it is 0, here it is negative maximum, again it is 0. This happened to be a triangular. So this is also a triangular waveform, but a different characteristics. 0 here, maximum there, and at the same time period becomes negative maximum and again 0. This also tries to exhibit an alternating waveform. Okay, so all these 4 or alternating waveforms with respect to a time period all possess a similar frequency, but the nature of the wave shape happens to change. So when we look at sinusoidal, it is going to be a continuous change. Any time interval if we choose, it is going to have a continuous change in magnitude. It reaches a maximum. After it reaches a maximum, it tries to reduce to 0 and negative maximum to 0. This is happening behind an alternating current. If an alternating source is being taken, it provides voltage and current with the same nature. Its continuous change in voltage, continuous change in current is going to happen for the particular frequency. So for a square waveform, we happen to see a maximum and again a traversal, negative maximum. This is also an alternating. So we have plus and minus here, plus and minus here, plus and minus. So all these 4 are alternating waveforms. I am not going into much details of all these 4, but we choose sinusoidal one. We have a benefit out of it. We have a greater efficiency when compared to all these. You may know at 15-20 years back, when we look at the inverters what we had in our home, the UPS or inverter system works on square waveform. That is, it tries to create a unidirectional DC, which is like this, from the battery getting converted into a square waveform. This is all happened 15-20 years back when we had UPS system, an inverter system in our home or anywhere, which provides square waveform rather than sinusoidal. But if you seek the latest inverter systems or UPS, you may find pure sinusoidal being notated. You can see at somewhere over the box it will be put as pure sinusoidal, which is it is trying to generate sinusoidal waveform out of the battery unidirectional DC. So we have switching arrangements inside, we have power electronic circuits inside. That is a different topic that we will come to for the next class. And now, as I said, the alternating source represents with respect to the nature of the waveform, we put a notation like this. This is sinusoidal, this is also sinusoidal. This is how an AC voltage sources are being represented. So this is all about the sources. Let me consolidate. So the first one is DC voltage source. If we say DC voltage, it is going to keep voltage constant, current varies. In a current source, current being kept constant, voltage varies. So this is the difference between both is going to supply voltage and current, but what is being kept constant makes the understanding different. So this is all about the sources. Okay. Now you must have understood what is a resistor, what is an inductor, what is capacitance, and how the relationship between voltage and current in a capacitor, inductor, etc. Now we will see what all the other equivalent components we will see in circuit analysis. This we call it as impedance. So what is impedance if you ask me? It is a collective combination of resistance plus inductive reactance or resistance plus capacitive reactance or collection of R plus JXL minus JXC. All sounds to be called as impedance and the unit is ohm. Now you must have understood why we are converting an inductance into inductive reactance, capacitance into capacitive reactance, so that we equate and find one particular component as impedance inside an AC analysis, AC electric circuits. Okay, so this is all about the next component called impedance. Why impedance is important, we will see when we go for an analysis in the circuit with respect to an AC source. Now coming to resistors. I have a resistance of 1 kilo ohm, say for an example. I put another 1 kilo ohm resistance like this. What do we call this? So next the topic is going to be about the realization of resistors in series and parallel. Say for an instance we have two 1 kilo ohm resistance which are connected in parallel. You say me how it is parallel. See, the current gets divided. Okay, if the current is constant, then we say it as series. Say for example, if the same 1 kilo ohm resistance being put like this, the current remains same 1 kilo ohm resistor, the current doesn't get divided or branched out, we say this as series, this as parallel. Okay, so now what happens if we have, say for an instance, 1 kilo ohm resistor in parallel and series, what is the effective resistance we get? So here the R equivalent is simply 500 ohm. I will tell you why it is 500 ohm. Whereas here the R equivalent will be 2 kilo ohm, even though the individual resistance value is 1k each. If we have two 1 kilo ohm resistors in parallel, the effective equivalent resistance is 500 ohm, and for the second in series connection the effective equivalent resistance is 2 kilo ohm. Okay, this is how a resistor behaves when connected in series and parallel. Say for instance we have 3 resistors in parallel. What happens then? This is also a parallel connection. This is also a parallel connection. This is R1, this is R2, this is R3. Then this effective R equivalent, what will happen to it? So the R equivalent can be given as 1 by R1 plus 1 by R2 plus 1 by R3. The same case here, when we have two resistors in parallel, R1 and R2, the R equivalent is given by 1 divided by 1 by R1 plus 1 by R2. So which is 1 divided by 1000 plus 1 by 1000. If we equate and find, the answer will be 500. Okay, clear? So that is the 1000 value is common, so we get 2 by 1000. If it gets inverse, it becomes 1000 by 2, which is naturally the value is 500 ohms. For an equivalent resistance of resistors in series, R1 and R2, we have R equivalent is given by R1 plus R2. And for three resistors in series, the R equivalent can be R1 plus R2 plus R3. So this is all about the realization of resistors in parallel and series. Okay, so in series connection, the effective equivalent calculations, and for the parallel connection, the effective equivalent calculations. Now we will see how this will affect a circuit. Now consider the circuit. I have 30 volt which is being connected to three resistors. R1, R2, R3. All three are in series connection. Now if a 30 volt source is being connected to it, now the current I tries to flow and create three drops across: VR1, VR2, VR3. So what is VR1? VR1 is nothing but voltage drop across resistor 1, which can be given by I times R1. Similarly, the voltage drop across R2, if we speak, same to same, and given by I times R2. Say for an instance, we have VR3. This happened to be the formula. Now, if R1, R2, R3 are equal, say let me take R1, R2 and R3 as same as 100 ohms or 1 kilo ohm, 1000 ohms. Okay, let me put it as 1k. What happens? Now each is 1 kilo ohm. Then how the voltage gets distributed? Now 1 kilo ohm into the current, we should find the current which is given by the supplied voltage divided by R equivalent. We know that the R equivalent for this is R1 plus R2 plus R3. So V divided by R1 plus R2 plus R3 given by 30 divided by 3 into 10 power 3 this becomes 10 into 10 power minus 3, or we can say it as 10 milliampere. So the current value is 10 milliampere. So if I want to find the voltage drop VR1, VR1 is given by I into R1, which is 10 in 10 power minus 3 into R1 is 1 in 10 power 3, which is obviously 10 volt. Similarly, when we go for finding VR2, which is 10 volt, similarly when we go for finding VR3, it is 10 volt, which is, the understanding is, if I have equivalent resistances, equal value of resistance inside one circuit, if it is in series connection, then the voltage drop is equal. So we get 10 volt drop, 10 volt drop. So by KVL, Kirchhoff's voltage law and current law, we can go for that afterwards, but for the realization I'm saying whatever the supplied voltage gets dropped here. So since three resistors are equal, we find equal voltage drop in between, 10 volt drop across each resistor. So this is the understanding how a series circuit is going to behave, series resistor network, if it is connected to a voltage source, how it behaves. So let me see, when a parallel circuit, say this is an example for a series. Next what we are going to see is for a parallel circuit. This is three resistors connected in parallel, okay, and I have a current source of 30 amperes, similar constraint, okay. Then what will be the current flowing through it? So this is I need to find out what is I1, I2, I3, all the three resistance R1, R2, R3 is equal to R3 is equal to some resistor, okay, some X value. Then what will be the current? Again you can find it like, for a current it is going to divide in parallel, so the values of I1, I2, I3 will be obviously 10 amperes, each 10 amperes. So the collective sum will be equivalent to that of the supplied current of 30 ampere. So a resistor, if it is connected in parallel, it is going to divide current which is being supplied. If a resistor, if it is connected in series, it is going to divide voltage if it is connected in series. So this is for the understanding of resistors, how it behaves in series and how it behaves in parallel. Similarly, we can calculate for each current through the branch, through number of formulas are available, we can use that, but for simple understanding I'm saying how the resistor behaves. Here the resistor is going to create a drop across each, since the values are same, the VR1, VR2 and VR3 is going to be constant, so we have 10 volt, 10 volt, 10 volt drop here. If it is connected in parallel, it is going to create a current division, equal current division of 10 ampere, 10 ampere and 10 ampere if the source is 30 amperes. So this is how the resistor behaves in a series and parallel network. So this is time again. So what we have discussed so far, I am going to consolidate. We have started from what is resistor, inductor and capacitor. We have understood how the resistor behaves, how the inductor behaves, how the capacitor behaves. We understood how the phasor relationship with each and every component, why we need all these three components to be clubbed together, and what are the types of sources which are present and available inside electric circuit. And later we went for understanding about how series connection and parallel connection functions. So this is for the introduction of electric circuit analysis. So next class we will move in detail further how to realize AC based circuits, how to realize different components, how to go for different analysis, voltage division rule, current division rule, network theorems, all comes afterwards. So this is all about introduction to electric circuit analysis and the components part as the first part of the our video. This is going to be the initial phase. So we'll go into the dive into the concepts in the upcoming videos. Thank you.